Hi, welcome back to Math as a Second Language, where today we're really going to get into fractions in more detail. But before I do that, I would like to talk to you a little bit about the difference between how mathematicians use the word equal and, well, maybe not the difference, maybe it's used the same way in society. For example, when the Declaration of Independence says all men are created equal, does that mean they all look alike? Do they all have the same height? Do they all have the same weight? They all have the same, whatever you want to mention. Doesn't it just mean with respect to the law? In other words, that just because you're poor doesn't mean you won't get the same justice if you were rich. If you don't have much power, you're going to get the same justice as the person who has power. See, we mean equal with respect to something. Now, for example, when you write that 6 plus 2 equals 5 plus 3, do you really think that 6 plus 2 looks like 5 plus 3? No, they're equal in the sense that what? They name the same number. And that was why in the new math, they insisted that you say 5 plus 2 is equal to. In other words, up until that time, people were saying 6 plus 2, 6 and 2 are 8. No, 6 plus 2 is 8. 6 plus 2 is a number, a numeral, that represents the number 8. Just wanted to make that distinction. The reason being that in dealing with fractions, we saw that in order to compare them, they had to have the same denomination. In other words, we couldn't just look at the 2 and the 3 in 2/5 and 3/8, because the 2 was modifying fifths and the 3 was modifying eighths. So the real question comes up is, when you replace a fraction by another fraction, how do we really know that they're equivalent? I don't like to use the word equal, that they're equivalent in the sense that they name the same fractional part. And that's what I want to discuss a little bit in today's session. For example, let's suppose we ask the question, which number is greater, 2/5 or 3/8? Now, if you use the number line, how does that work? We'll call this the number line. And we'll look, and this will be 1 unit. The whole number line is 1 unit. And in fifths, what do? We break the number line down into 5 pieces of equal size, and 2/5 would then be, say, this size over here. Or these 2 pieces, either way. And how would we find 3/8? Well, now you divide that same length into 8 equal pieces, so that even though you're taking 3 of them, we don't know for sure whether these 3 pieces add up in length to more than these 2 pieces. So what we had to do was to find a common denomination. And what you would do in that case is you say, well, look, here I need my cornbread to be divisible by 5. In other words, I need it to be sliced into 5 parts of equal size. Here I need eighths. Well, you see, if you try to do this just with the number line alone, you say, okay, this already comes in 5 pieces, so I'll divide each of the 5 pieces into 8 pieces. This already comes in 8 pieces, so I'll divide each of the 8 pieces into 5 pieces. And can you see how cluttered this is going to become? Students have a hard time visualizing this. Look what happens when we use the cornbread model. We're still trying to compare 2/5 versus 3/8. So what do we do here? We say, okay, if we want the number of pieces to be divisible by 5 and also to be divisible by 8, let's take the cornbread and we'll divide it into 8 pieces of equal size, let's say the vertical slices, okay? And then we'll horizontally divide the cornbread into 5 pieces of equal size. So what is 2/5 of 40 pieces? 2/5 of 40 pieces, well, here's your 2/5. See, 1/5, 2/5. Each of these is what, 8 pieces? See, we want 2/5 of 40 pieces. So this is 8 pieces, and this is 8 pieces. That would be 16 pieces. Okay? And what would 3/8 of 40 pieces be? Well, the eighths are going this way, so we want 3/8. Each eighth is 5 pieces. See, 40 divided by 8 is 5. And we're taking 3 of those pieces. Now, we couldn't compare the 2 and the 3 here because they were modifying different nouns. But we can compare the 16 and the 15 here because all the pieces are the same size. So in other words, 2/5 of 40 pieces is 1 piece more than 3/8 of 40 pieces. By the way, we're not going to do this quite yet, but I did want you to see what this really says in terms of the arithmetic of fractions. It says if you take 2/5, it's what? It's 1 piece more than 3/8. So how much bigger is it? A piece is what? 1 of what it takes 40 of to make the whole cornbread. And this, to me, is relatively easy for students to see. This, to me, seems to be the stumbling block that most students have. In fact, they look at the numerators and they think, what? I'm taking away more than what I have here. But that's like saying 2 dimes minus 3 pennies is 7 cents. You're still taking away 3 pennies from 2 dimes. So at any rate, I thought that this would be a nice segue to get into. But how do we look at this from a different point of view? In other words, how do we know, for example, that I learned mechanically, if you want to get from one fraction to an equivalent fraction, you just multiply numerator and denominator by the same whole number. So if somebody wanted me to convert 2/5 into 15ths, I would say 5 goes into 15 3 times. 3 times 2 is 6. And what I really did was, when I said 5 goes into 15 3 times, I was multiplying the denominator by 3. And then when I said 3 times 2 is 6, I was multiplying the numerator by 3. And what that was saying, in reality, was if you multiply numerator and denominator of a fraction by the same number, you get a different fraction, but it names the same number. So for example, here's 2/5. How could I see how many 15ths this would be? Well, for example, couldn't I divide each of these pieces into thirds? And now the 5 pieces have become 15 smaller pieces, right? And these 6 pieces, each bigger piece, has become 3 smaller pieces, and that's why I multiplied numerator and denominator by 3. What I would like to show you is that if you use the cornbread model, all you have to do is say, okay, here's my 2/5. All I'm going to do now is horizontally divide this into 3 equally sized pieces. I think this will just about do it. And now what do I have? I still have these 3 pieces, these 2 pieces here, these 2 big pieces, but they're also what? 6 of the smaller pieces. In other words, 2 of the big 5-piece thing are equal to 6 of the smaller ones. And you can see this right away from the diagram. So again, if you wanted to not draw the cornbread and compare this, see what we just did over here? We multiplied the 2 and the 5 by 3 and said 6/15ths, and 6/15ths doesn't look like 2/5, but they name the same rate, and we'll show that in terms of a physical example momentarily. Now, what did we do before? To compare the 2/5 and the 3/8, we divided the cornbread into 40 equally sized pieces, and then we showed that 2/5 was 16 of those pieces, and that 3/8 was 15 of those pieces. Well, that was pretty easy to see, but watch how this thing looks formally. You said, okay, to compare these, we need a common denominator. Since the denominators are 5 and 8, a common denominator will be 40. Notice the mechanical way in which I was taught. 5 goes into 40 8 times. 8 times 2 is 16. 8 goes into 40 5 times. 5 times 3 is 15. And notice that 16/40ths, see, what was 1/40th in our diagram? Wasn't that 1 piece of the cornbread? See, in terms of the cornbread, this is 16 pieces. Okay? Now, if this is too abstract, we go into what I call the unit pricing model, where we say, okay, suppose in one store they're selling 2 pens for $5. In another store they're selling the same pen at a rate of 3 pens for $8. And you want to find out which is the better rate, meaning the cheaper rate. Okay? And you say, well, I can't compare these because the 2 is modifying 5 while the 3 is modifying 8. So you say, well, the common denominator would be 40. And to get from $5 to $40, you'd have to multiply by 8. So you might write something like 2 pens times 8 equals $5 times 8. And if you want to see this verbally without the magical formula of just saying multiply both by 8, you're saying, look, if I get 2 pens every time I spend $5, if I spend $5 8 times, I'm going to get 2 pens 8 times. That gives you a way to visualize why the fraction didn't change if you multiplied numerator and denominator by the same whole number. Now you do the same thing with this number over here. You say, okay, for $40, 8 goes into 45 times. So what I'll do over here is I'll multiply numerator and denominator by 5. Now what do I wind up here? This is 16 pens for $40. This guy is 15 pens for $40. And what this says, without any reference to, notice this looks like a fraction, but I'm just using this to abbreviate or to rewrite 2 pens per $5. And what this says is, hey, to compare these two, for every $40 you spend, you're going to get 16 pens if you buy at this rate, but only 15 pens if you buy at this rate. In other words, for every $40 you spend, you get one more pen if you buy them at this rate than if you did at this rate. And that's what this means, sort of. Do you sort of get the idea? You can start from the cornbread. From the cornbread, you can get to the rote memory type of recipe, but now it won't be rote memory because they'll be able to associate that with what happened to the cornbread. And then to cement it down, you give a real physical problem to show how this works in the real world. So in summary, what we did was we showed that 2 common fractions are said to be equivalent if they represent the same number. Given a common fraction, we obtain an equivalent common fraction by multiplying or dividing the numerator and denominator by the same non-zero number. Notice, by the way, I did things in terms of multiplying. Remember what I said? I said, like, to get from 2/5 to 40ths, you multiply both by 8. Well, you know, we tend to read formulas and equations from left to right. Read it from right to left. What this said was 16/40ths is equivalent to 2/5. And how did we get 2/5 from 16/40ths? We didn't multiply both by 8. We divided both by 8. But be careful. Keep away. Don't allow the students to say, if I do the same thing to top and bottom, I will always get an equivalent fraction. Be very careful about that. For example, if I start with 2/5 and I multiply numerator and denominator by 3, I get 6/15. And these are equivalent, aren't they? If I can buy 2 pens for $5, if I spend $5 3 times, that's $15, I will get 2 pens 3 times, that's 6 pens. But look what happens if I add 3 to both the numerator and denominator. The 2/5 becomes 2 plus 3 over 5 plus 3, that's 5/8. And 5 out of 8 is not the same rate as 2 out of 5. And in fact, to see why these are different, did you notice? Remember we talked about the same difference before? When I added the 3 to both the numerator and denominator, didn't the number of pieces between the numerator and the denominator stay the same? In other words, here the difference is 3. Here the difference is also 3. What this says is if I divide the cornbread into 5 pieces of equal size and take 2 of them, okay, there will still be 3 pieces left. If I divide it into 8 pieces and take 5 of them, there'll also be 3 pieces left. But the 3 pieces that are left when I divide the cornbread into 8 pieces are smaller than when I divide it into 5 pieces. So in other words, when you add the same number to numerator and denominator, if the fraction was less than 1, you actually get a bigger answer than what you started with by adding on the same to the numerator and the denominator. And again, for a concluding remark here, notice again psychologically why I like to start with pieces of the cornbread, then wean the students away from that into fractions, because look at how much more colloquial it sounds to talk about pieces of the cornbread as opposed to saying halves, thirds, fourths, and fifths. In other words, I can say the piece you get if you slice it into 2 pieces of equal size, 3 pieces of equal size, 4 pieces of equal size, etc. But at any rate, let's conclude for today with our usual practice problem, where I will ask you to pause the video, read the question, give me the answer, and come back and see how I did the problem. And the practice problem today is find a common fraction whose numerator is 30 that is equivalent to the common fraction 2/5. Well, what did I say the problem was? I want to get an equivalent fraction where the numerator is 30. What did I do to the numerator to get to 30 in terms of multiplication? See, don't say I added 28, so I'll add 28 here. We saw that you don't get equivalent fractions that way. It's with respect to multiplication. I would have to take this 15 times, but if I multiply the numerator by 15, I also have to multiply the denominator by 15. So this says 2/5 is equivalent to 30/75. And in terms of the pens problem, if I can buy 2 pens for $5, at that rate, I'll be able to get 30 pens for $75. And be careful that the answer depends on whether it's the 30 is in the numerator or in the denominator. For example, if the denominator is 30, that says to get from 5 to 30, I had to multiply by 6. So I got to multiply this man by 6. See, this one says to me, if I'm buying 2 pens for $5, how many pens do I get for $75? And the answer is 30 pens. This one says, if I get 2 pens for $5, how many pens did I get if I spent $30? And the answer is 12 pens. So you start to see, again, how much the language of common fractions is just a different way, in fact, a way of almost abbreviating the commands we would have to give if we insisted that everything be whole numbers. But that ultimately we can convert all fraction problems into equivalent whole number problems. And so if the youngster really learns to understand whole number arithmetic and also learns to understand the adjective noun theme, they will never have to learn anything new to do fractions. And I think that brings us to the end of today's lesson. I will see you all again next time. Meanwhile, stay well, have fun, work hard.